So, well, good afternoon, everyone, and thank you to organize this virtual workshop. So we'll continue here on focal plane wavefront sensing, here using machine learning to perform the measurement. So we've heard all about the advantage of focal plane wavefront sensing, that is the eye sensitivity, but it's also very simple optomechanically. And if you use your science camera to perform the measurement, well, you don't have non-common path aberration or chromatic errors. Now, the downside is that it's typically, it requires a lot of computation. And as we've heard as well in the various talks, there's a phase ambiguity. Here you have another illustration, and you need to lift it by some means. And there are many ways of doing that. Now, there are several regimes, and again, we've heard several regimes where we could use focal plane wavefront sensing. Here, I'm sort of comparing two possible regimes. One is the non-common path aberration measurement, and the other one would be adaptive optic correction. And so those numbers are to take with a pinch of salt because some of them are depending on the wavelengths, but it's just to compare them. As you can see, so non-common path aberration, typically you want to measure relatively low level of aberration and on a limited number of spatial frequencies. And so in terms of dimensionality, this problem is simpler, let's say, than the adaptive optic correction. On the right, you have a simulated image behind a vortex corner graph. And here well, you can distinguish this well-corrected region. And inside, you have speckles and extended features that are due to quasi-static aberration. And as was mentioned in the previous talk, they are detrimental to the contrast and so to our ability to detect exoplanets. So that's something we want to correct and at a stable level. There might, of course, be other applications. Well, we've heard about the low wheeling effect, which would be yet another thing, or as well the cophasing of segments. But here in this talk, well, we'll take more the case of NCPA correction. So when you do machine learning, it all starts by a data set and a large data set. So here you have the key parameters of simulation. So they are quite simple simulations. So we generate phase map that we propagate, and we have in and out of focus images. And we consider different level of aberration. So I will talk about low level of aberration, talking about 70 nanometers. While high level of aberration will be 350 nanometers. And we also consider 20 or 100 Zernike modes. Now, the way we generate the data and the distribution that we choose, of course, will dictate the way our models, the CNN will behave. So here we have a polar distribution over all spatial frequencies, but each individual mode is drawn from a random distribution. So you have the example here on the plot below. So for the architecture, so we've picked, actually we tested at the onset of this study, several architecture. At the end, we use essentially UNet and ResNet, which are readily available on internet to perform classification. And we just modified the last layer to perform regression instead of classification. And so, we use ResNet to actually infer vector of coefficients, of Zernike coefficients, and UNet here is adapted to perform phase map, or to return directly a phase map. And yeah, the loss function is just the classical MS error. But before I present results, of course, there's a question of metric. How do you evaluate how good your model is? Well, that might depend on the application. So. And here in the following slides, I will discuss two aspects. One is the sensitivity limit, so how accurate can you measure the wavefront? And then I will explore different robustness of the CNN. So the sensitivity limit is ultimately given by nature of light, so it's photon noise, and actually we only simulate photon noise in the study. And if you have only that, the amount of information you can extract, well, you can derive a limit which was derived by Patterson, and the variance is basically bounded by this 1/4 times the number of photons per independent mode. And that's actually a limit you can also find using the uncertainty principle. Now, having this bound doesn't mean you can reach it. And today, the most sensitive detector we know of is if I make no mistake, the Zonic wavefront sensor, or the iQuad, which is probably similar. And it's a factor 2 away from that limit. Focal plane wavefront sensing is not that far, but it's a little bit less sensitive, and so yet a factor 2 away from this variance. And so in the next slides, in my plots, I will be using this limit, which is a sum over all the number of Zonic I'm using. Okay, so results. So I'm going to explain this in some detail. So you have this plot show you the error, the wavefront error as a function of number of photons you have in the image. And each point here uses a different model. So it means it's a different training and uses different data sets for evaluation. So the first thing you can see is that in a large flux range, we are able to reach this theoretical limit I just mentioned. And only at extreme, we see the departure from that limit. So on the right side, when you have a large level of aberration and a large flux, we sort of reach a plateau here that we believe is due to the size of our training set. Now on the low side, and for low aberration, we also converge flatten to 70 nanometer RMS. And that's just because we are giving a prior information in our training and in the test. Yeah, I've also mentioned here magnitudes for reference. Now, having the sensitivity, of course, is nice. And then we've looked at several aspects of the robustness, how it might behave with changing parameters compared to what it was trained for. And here I'm illustrating this to look how it behaves when you give PSFs that have a different amount of aberration with respect to what it was trained for. And what you can see from those plots is that when the PSF have a lower level of aberration, the accuracy is there fairly constant, which is of course good. And when you go to higher level of aberration, then the inference quickly decrease. So I must insist here that all this is performed in one step, of course, so it's not iterative. Now from that, we can do the experiment to see how iteratively it does behave in what might be a more realistic application. That's what I'm illustrating here. So you have the error as a function of number of iteration, and I've been giving the CNN increasing level of aberration. And you can see that at first it reached its optimum in only a few iterations and then stayed there at a constant low level. And of course, when you further increase this, it starts to stagnate and eventually to diverge. But still, I think it's a fairly encouraging result, but because if you look at the PSF themselves, the PSF at 300 nanometer or so, it doesn't look at all to a PSF with 1 micrometer RMS. And so it's to some extent remarkable that it's able to converge with such different PSF. Well, then we'll look at different kind of disturbances. So as I mentioned, so far we look only at photon noise, and of course it's highly idealistic. And in the image we can expect higher spatial frequency to be present. And here we just did a simple experiment training our model with 20 Zonics and then testing this on the dataset with 100 Zonics. And so you have here the error projected as a function of Zonic mode. And in the low aberration regime, you can see in green that we perform a good measurement and we're not that far from the theoretical limit. But when we ramp up the aberration level, we see that we have a bigger gap that's building up. And basically those high order disturbances start to disturb this measurement process. And effectively, we will be better off with a higher photon noise in this case. But then, of course, we can adapt the learning strategy, and that's anyway will be a conclusion of my talk, is that, yeah, we can pick how we train it to make it more or less robust to different conditions. Because I mentioned at the beginning, so for phase diversity, we also do the short experiment training the CNN using only one PSF, for example, in focus here in orange. So that's the same error as a function of zoomed modes. And we see that the even mode has not probably sense, while the odd modes are still fairly well measured. And if we use a single PSF with a high defocus, here we have a prior on sign, and so we leave basically the ambiguity. Then I wanted to give a word on the commercial cost. So ResNet and UNet are fairly big architecture, and you have here the number of flops required to do one inference. So this is probably another problem for NTPA measurement. But when you go to EO application at 1 kilohertz, well, you start to speak about tens of teraflops. And although that might be doable from the commercial standpoint, it raises many issues in terms of implementation. Yeah, one experiment I wanted to slightly show, well, quickly show is we will try to add a layer to our ResNet, a mixture density layer, to actually not predict coefficient, but to predict probability distribution. And we did this in an experiment to basically have the sign ambiguity become explicit in the outcome of the CNN, and as well to have directly an information on the error we're doing. And so you have here an illustration of what we can get. So this is for focus mode, where with a single in focus, then you probably retrieve the amplitude, but not the sign of the mode. So we did a number of other analyses that I'm happy to discuss offline, looking a bit at the effect of pixel scale, signature noise, the size of the training set. We also tried to apply this to a vector vortex chronograph PSF and compare this to standard iterative algorithm. So my conclusion is, I think, as I tried to show you, is that we can reach optimum sensitivity with the CNN, and it's quite robust and flexible. And the flexibility comes by the fact that you can adapt your training strategy depending on the problem you want to solve. And it's probably good to mention as well that you can always retrain a model as well. So you can adapt something, yeah, you train first on simulated data. Yeah. And well, of course, so far it has been only simulation. We started to look at lab data. And the question here is really how much we can rely on simulated data and how much we need real data to perform the training. And that's something we'll look in the future. And yeah, and then you always need a source of diversity or prior. And it's also something we will look at for eye contrast imaging. Thank you very much. And I'm happy to try to answer your question.
Thank you very much. We have several questions, I think, for you now online. So the first one is regarding spectral bandwidth. So they're asking, what about the spectral bandwidth of this wavefront sensing method, and how can it be increased?
Yeah, so far it has been monochromatic, the simulation we've done. So it's highly idealistic. And since now we're starting to look at laboratory data, we have some level of non-chromaticity. So I think it's just a question of the training and how much that will impact maybe the need for the training size. And then we can expect that we can extract essentially all the information that is within it. So I don't expect to have a big difference to, well, any other sensor, let's say.
Okay. And then we have a few popping up here. The next one would be, I may have missed it, but do you have a paper where we can read more?
Not yet. We're trying to wrap up a first one on the simulation. Yeah. So okay. I hope in a few months we'll get one out.
Excellent. Our third question is, how well did machine learning do relative to a Gershberg-Saxton approach?
Right. Had no time to show the plots. So here I did a comparison using, so again, two images, one in focus and autofocus, and so slightly modifying the very standard Gershberg-Saxton. Well, basically, if you are Nyquist sampled, well, at least what I found and using my implementation, that if we are Nyquist sampling the PSF, both reach a similar level of accuracy, just that the Gilles-Saxon needs 10 or 20 iterations to reach that level, while, well, in the regime we've tested with 1 iteration, we could do it with a CNN. Now, the situation was less clear to me when we were starting to have a different kind of pixel sampling. And, well, it's not entirely clear if it was specific to my kind of implementation or if it's a generic effect. But so basically, the accuracy given by the Gilles-Saxon was decreasing as we were increasing the sampling.
Okay.
But well, there are several effects that come into line. So that's, yeah.
Okay. And so you would say that this does better than the Gilles-Saxon, even though they'll reach the same level, you can do it much quicker than a Gilles-Saxon iterative scheme, correct?
Yeah, well,
that's what you said. Okay.
That's a yes, but then formally speaking, one will have to evaluate the computational need, so it may be a bit biased. And as of course, as well, we don't need to do any phase unwrapping, for example, so that problem is somehow,
right.
Not present here.
And so I think we're done with questions from the Slack, but I had a question. You were showing results with training with Zernike modes, correct?
Yes.
Have you tried other types of modal basis sets, or is there a reason to try modal basis sets, or do you think Zernike's does well enough?
Well, so far we didn't see a reason because it's a relatively generic study, let's say.
Mm-hmm.
It just makes sense to us to use a model basis with independent, well, orthonormal modes. I guess can level will behave similarly well. But
yeah. Okay. Well, I think then we are well within time and no current questions. So thank you so much.
Thank you very much.